Problem solving and model building. So if we're going to work with big data and complex models, then we really need an approach to solving problems that allows us to build good models. Remember, our goal is the true model. So notice that very often in this course, we're going to have three sets sampled from the true model plus noise: a training set, a validation set, and a testing set. The training data will be used to develop the model. Validation will be used to test during development of the model itself, after which the testing data is used to determine how good the actual final model is. Supervised learning is validation while learning parameters during training, and then you test afterwards. And often the test set that you use is called a gold standard. Very often it's a set of data that you've held back until the actual final test. So complexity, bias, and variance will never know the true model. Too many variables. Noise obscures direct observation of the true model. An equation model has only a few variables for very often high bias and low complexity. An algorithm model can have very many variables, but it also is often very complex and has high variance. Equation models, therefore, often need to be more complex. Algorithm models often need to be more biased. So choosing a model and modifying its bias and complexity is problem dependent. There is no always do this approach. You have to have a problem solving approach where you can look at your problem and figure out by diagnosing the problem what you need to solve the problem itself. And we're going to use Polya's method. So in 1945, he developed a method called How to Solve It, based on developing strategies for each step of the problem-solving process. So here is Polya's method. No, it's not. These are obvious. Polya's contribution was to define and develop strategies for each step. So here's how we go from understanding to devising, exploration, devising to carrying out, so on and so forth. And in data science, that includes these in certain tasks. The first task is to explore the data, get up close and personal. This uses pre-processing. Modern data is messy, and we often have to pre-process before we can even understand what kind of a plan we can carry out. Now, often we say that a problem is a question, and therefore our goal is to refine and revise the question until there is a plan. Most data requires pre-processing. Now you may say, well, we didn't need it for the calculus grades data. Well, all the exams had the same units and scale, but because of our lack of pre-processing, we didn't have a good understanding of the parameter values. So here's our logistic regression model. The exam scores were on a 100-point scale, but the previous was on a scale of either 0 or 1. Look at our parameters. Beta naught is the largest parameter value. Is there something significant there? Well, this is misleading because all of these are on different scales. So let's rescale all the variables to go from 0 to 1. So the exams are going to be now on percentage scales, and the previous is from 0 to 1. And now what kind of parameters do we get? Now the smallest parameter is beta naught. For example, we often have to convert big data into numerical arrays. So this data is not numerical, the major is not. So we can convert it to numerical using one-hot encoding. Notice we don't want to say 1, 2, 3 for the major because that would imply a ranking. We simply want a numerical representation. A lot of times we use matrix multiplication. So this is just a review of what we mean by matrix multiplication. It's just taking inner products of rows of the first with columns of the second. And that's what we call matrix multiplication. We often have to rescale feature columns. Notice that in this data set, chemistry, physics, math, and height, all of those things are less than 2. But age is all over 18. So that means this age column could completely dominate everything. So we can change it. So instead, maybe say it's the number of years past the age 18. So which method do you use to rescale? That's why we explore and reprocess. It's important to note we may not be able to use matrix arithmetic. A here is a square array of numbers, and you might be tempted to say, well, we can square it, but A has units. It's not a matrix. So we have 19 years and 1.65 meters. So when we get a product, our units are nonsense. Squared years, years meters, what does it mean to add a meter to a year? But we can always think of a rectangular array of numbers as being the product of matrices. But we can always factor it into matrices. So this is called matrix factorization. How do you know which to use in your project? Well, you're just going to have to explore. So the pre-processing methods you use will be a coordination of the question you're trying to answer and the data you have to answer it with. So there's always going to be some bias when you do pre-processing. So let's go back and look at our unstructured tweet data. We have a question about whether or not we can predict positives or negative tweets. And so we're going to have to explore, understand the problem, ask a question, revise. Just keep doing this until we have a plan. So what causes a tweet to be positive rather than negative? Well, here's our data. Notice that our sentiments can be positive, negative, neutral, or irrelevant. We're only going to use positive and negative. It's a small data set chosen to demonstrate the value of exploration. Now, we're going to look only at frequently used words. So let's look at this Python code. Notice we're only going to keep words that occur at least 10 times, and we're not going to use words with @ symbols or hashtags. So these are the frequently occurring words in our tweets. So a revised question is, how does word usage differ between positive and negative tweets? If we look at the positives, here's the word usage sorted by positives. Here it is sorted by negatives. And notice that you have differences. So you have a and not corresponding to our frequently used in negative tweets, and ice cream sandwich is common in positive tweets. So here's some actual tweets. And so we should be considering how words are used in individual tweets. So what words in a tweet cause it to be positive rather than negative? Let's look at a new structure. Words as features and tweets as observations. And the coefficients of this structure will be the count occurrences of a given word in a given tweet. Now, those of you who may have seen something like this before, you may have just mindlessly said, let's take out all the stop words. And don't do things unless you have a reason to do them. So unmotivated removal of stop words removes the word not, and not's going to be an important word in our application. So we're going to keep words that occur at least 10 times and appear in no more than 200 tweets. So most of the counts are 0. In other words, the count array is sparse. So why do we do this? Well, it eliminates the stop word "the," which occurs in practically every tweet, but retains the word "not" and other words that are important to differentiating between positive and negative tweets. Where do the 10 and 200 come from? Well, we just had to do expiration. So now we're suggesting that the rows of the count array can be used in place of the corresponding tweets. Now we need a representation. So we want to engineer this representation until it allows us to carry out the plan that we devised earlier. So expiration reveals tables of word counts are not all that effective. For instance, how do we differentiate between long and short tweets? Well, what if we used word frequency rather than actual counts? And a word that occurs in a whole lot of tweets has a very high count, but doesn't predict very much. For instance, if we had not removed the word "the," it occurs in practically every single tweet, but has no ability to predict whether or not we have a positive or negative tweet. So we end up with what's called the term frequency inverse document frequency representation. And in here, we have percentages, word frequencies rather than actual counts, and we have a penalty for words that occur in a very high number of tweets. It's still sparse, most of the coefficients are 0, but now we can move on to a model. So a model is, of course, representation combined with computation. The computation is via functions. So we need models that are simple enough we can understand them, but complex enough to represent underlying structures. And we're going to use nearest neighbors. Nearest neighbor methods are in artificial intelligence are decades old and highly reliable. Robotic arms, classification, regression, they're intuitive, high model complexity, and low bias. So nearest neighbors are on the other side with respect to logistic regression. So despite its simplicity, nearest neighbor have been successful in a large number of classification and regression problems, foundation of many other learning methods. And in some sense, all of machine learning predictive modeling can be derived from nearest neighbor relationships. They're ubiquitous. Much of what happens in machine learning is based on nearest neighbor methods either directly or abstractly. So how are we going to use k nearest neighbors to predict an unlabeled tweet? Well, given a row or tweet, we just find its nearest neighbor based on row similarity. If the neighbor is positive, predict that the given is also positive and vice versa. And when we do that, we end up with an accuracy of about 70%. So for this data set, we can predict a positive or negative sentiment about 70%, and we could improve this up to about 80% of the time. But this isn't satisfying. It's just the result of our carrying out the plan. The final step in Polya's method may be the most important of all: interpretation. So let's notice that we can actually make this prediction of positive or negative using only 42 words. That is, Polya's method led us to the 42 most important words in our data set. And this critical final step is to explain the importance of those 42 words. And I can do that with word clouds. So here you have a visualization of what it means to be a positive tweet, what it means to be a negative tweet in this tweet data. So exploration's the first step. Refine a question until you can answer it. Explore until you have a plan. Problem-solving approach is essential. Ultimately, it'll allow us to build complex models that use bias variance trade-off. And again, it starts with exploration.